So chemical formulas tell us how many atoms of each element are in either a formula unit or a molecule. We can also get some other information from the formula. Things like a mass percent, sometimes called a mass percent composition. So that tells us how much of this compound's mass is from a single element. And this is following the general idea of percent, which is this. The percent is the part that you're interested in divided by the whole thing, multiplied by 100 to make it a percentage. Now, when I saw, I don't know what they're teaching you in school these days, but people do weird things with percentages. So we had an equation like this for percent error, where you took the difference between the two measurements and divided by 1 times 100. And some of you then multiplied the answer by 100 again. You only multiply by 100 once, okay? And technically, percent here is the unit, okay? This is not multiplying by 100%. Don't use the percent button on your calculator. Just multiply by 100. Percent is the unit. So we can find the percentage of each element in a compound by mass from the formula for the compound, or empirically by experimentally analyzing the compound and finding its mass. And we're going to do both of these. So from the formula, what we do is just to make it easy, we choose to look at 1 mole of the compound, and we figure out how much mass of X is in 1 mole, and divide by the mass of 1 mole of the compound, which is the molar mass. Multiply by 100. The experimental mass analysis, you're actually taking a sample and weighing it, and then you're destroying it and figuring out the mass of one of the components. And so you have 2 pieces of data, and you just take the mass of the element and divide by the mass of the compound that you started with, times 100. Now, the percent of each element, if you add those percentages together, it should add up to 100%, right? Because of rounding and experimental error, it doesn't always come out to exactly 100%. And we need to be okay with that. Let's do an example. Acetic acid is the active ingredient in vinegar, C2H4O2. Calculate the mass percent composition of oxygen in acetic acid. So there's no numbers in this problem other than the formula. Calculate the mass percent composition of oxygen. So we're looking for the percent of oxygen. That's the part over the whole times 100. So the part we're interested in is oxygen. So how many grams of oxygen in a number of grams of C2H4O2? And then we'll multiply by 100 to make it a percentage. It's the part divided by the whole. The easiest thing, you could do it with other amounts, but the easiest thing is just say, well, let's look at a mole of this compound. The percent composition does not depend on how much of the compound you have. It's an intensive property. So choose 1 mole. Okay, so what's the mass of 1 mole of acetic acid? Well, we just learned how to do that, right? It's 2 times the molar mass of carbon plus 4 times the molar mass of hydrogen plus 2 times the molar mass of oxygen. We got 2 times 12.01 plus 4 times 1.008 plus 2 times 16 equals 60.052. grams per mole. Well, we're choosing 1 mole, so 1 mole of this weighs 60.052 grams. So we're going to put that in the denominator. That's the mass of 1 mole of the compound. And then we need to know what's the mass of oxygen in that compound. Well, we kind of already have that done for us. It's this part right here. There's 2 moles of oxygen in 1 mole of the compound, right? So this equals 24.02. Great. Thank you, yes. I don't know what I'm doing. I'd like to say I did that to test you, but I didn't. I was just being dumb. Thank you. This is the oxygen, not the... I was doing carbon. I don't know why, because it was first. This is the oxygen. Okay, so the mass of oxygen is 2 times 16, so it's 32.00. So there's 32 grams of oxygen in 1 mole of the compound. So that's what goes up here, 32.00 grams. Now here, the molar masses are going to affect the outcome of sig figs. I'm not going to try to trick you on problems like this, but the 2 times 16, this would have 4 significant figures. This one you could argue 4 or 5, but the 4 is going to limit it anyway, so we don't have to fuss about it. So 32 divided by 60.052 times 100, 53.2871%, 53.29%. In a percentage, the units go away, they cancel out, because here you have mass of one component divided by mass of the whole thing, and so those units are going to cancel out. And this is the unit on 100%, and so that's our unit here. So 53.29% oxygen in acetic acid. Any questions? We can use a mass percent as a conversion factor. So percent means the part over the whole times 100. We can also describe percent as how many parts out of 100. Percent literally means per 100. So how many parts per 100? So if we are given the information that Freon 112 is 69.58% chlorine by mass, that means it's 69.58 grams of chlorine out of every 100 grams of the compound. So we can take that percentage and make it into a conversion factor. What mass in grams of iron 3 oxide contains 58.7 grams of iron. Iron 3 oxide is 69.94% iron by mass. Well, we've got 2 numbers here. We've got 58.7 grams of iron, and then we're given a percentage, 69.94% iron. Let's write that in a different way. That's 69.94 grams of iron out of 100 grams of compound. So it didn't give us the formula, but we could figure it out. Let's do that real quick. So iron 3 is Fe with what charge? 3. That's what the Roman numeral says. And oxide is oxygen, and what is the charge on an oxygen ion? 2 minus. So to put those together, we're going to need Fe2O3. Do we need to know that for the problem? No, we actually don't. but I don't want to write out the name down here. Fe2O3. So that's what the percentage means. Because in real life, my son's kindergarten classroom, my oldest son, was 75% boys. Doesn't that sound fun? So that means if there were 100 children, 75 of them would be boys, right? Of course, there weren't 100 children. There were only 20. But 75% were boys. So that's what percentages mean. So we've got this thing and we've got that thing, and what are we trying to find? Grams of the iron 3 oxide. So we're looking for grams of Fe2O3. So we could start with this number, or we could start with this one. This is per, isn't it? Anytime you've got per in there, it's probably a conversion factor. So grams of iron to grams of Fe2O3, those are the units in there. So that's our conversion factor. We can do this in one step. 58.7 grams of iron. We're going to have grams of Fe2O3 on top and grams of Fe on the bottom. Here it's important that we specify grams of what, because otherwise we're going to get confused. Grams of iron and grams of the iron 3 oxide. So we got the units in place, and now we look at this fraction that we made here, and we put the numbers with the units in the fraction, come on pointer, in the other one. Oh, okay. It's got a life of its own. So 69.94 goes with the iron, so it goes in the bottom. And 100 grams of the compound goes on top. In a percent, so 69.94%, that has 4 significant figures, right? So when we write it this way, what we mean is 69.94 with 4 significant figures per exactly 100. This 100 falls into that exact category of a whole number as part of an equation. So we've got 4 sig figs down here, and we've got 3 there. So we do the math. 58.7 times 100 divided by 69.94. And I'm going to keep 3 significant figures, 83.9. Write down 2 extras. And then round that, 83.9 grams of Fe2O3. Any questions? This is not the only way to solve this problem. Some of you have a good understanding of percentages, and so you can do this maybe a little quicker. That's great, but you don't need my help. We can also get conversion factors from chemical formulas. The formula gives us relationships between how many atoms. Okay, I'll just start over here because I lost my Wi-Fi. We've got inherent relationships between numbers of atoms and molecules, or moles of atoms and molecules, in a chemical equation. So if we look at this compound, C2Cl4F2, in 1 mole of this are 2 moles of carbon. It's just in the formula there. C2 means there's 2 carbons in 1 molecule, 2 carbon atoms, or 2 moles of carbon in a mole of the compound. Or we could look at the fluorine. There's 4 fluorines in the molecule, so there's 4 moles of chlorine. I said fluorine, didn't I? 4 moles of chlorine in 1 mole of the compound. What would the relationship for moles of fluorine to moles of compound be? Two, because it's F2. Okay? So 2 moles of fluorine per 1 mole. So chemical formulas give us relationships in moles. They do not give us relationships between masses in grams, but they give us the moles. Okay, let's do this one. Determine the mass of oxygen in a 7.2 gram sample of aluminum sulfate. So we can write the number down. We got 7.2 grams of aluminum sulfate, and we're trying to find grams of oxygen. What are we going to need here? We're going to need the chemical formula. Right, we're going to have to look at the formula for aluminum sulfate and find out how many oxygens are in a unit. So this is an ionic compound because aluminum is a metal. So then we look at ions to figure out the formula. So aluminum 3 plus, yep. 3 plus because it's in group 3. And then we memorize sulfate. It's 2 minus, but it's not SO3. It's SO4. So very close. A good thing to do when you're doing problems like this is try to get it from memory and then check, okay? Try to get it from memory and then check. And so that'll just help you to get more comfortable with these. So then putting those together, we could do the crisscross thing, and we're going to end up with Al2 SO4 3. So now we know that there are 12 oxygens in 1 unit of that. So that's going to allow us to convert between grams of oxygen and grams of aluminum sulfate? No, moles, right? So we've got grams here. Now that we know the formula, let's write the formula in there. Al2 SO4 3. Yeah, so we have to find, we've got the grams, we need to find the moles. Here we're going to have moles in the middle. We're going to have 2 moles in the middle. We're going to have moles of aluminum sulfate. And I did not leave enough room, so I'm going to erase that. And from that formula, we can convert from moles of the compound to moles of oxygen. And then using the molar mass of oxygen, we can convert to grams of oxygen. You might say, well, isn't there a shorter way to do this? Not really. Okay, so here's a question that comes up sometimes. This oxygen, should that be O2 or just O? Because oxygen is one of those diatomic elements. Well, is the oxygen by itself or part of a compound? Well, here it looks like it's by itself, but we're asking how much oxygen is in the aluminum sulfate. So this oxygen is in the compound. So it's not by itself, it's in the compound. Those diatomic elements are like junior high girls. They don't like to go anywhere by themselves. I don't know if girls, you remember being in junior high, you always went to the bathroom with a friend at school, right? Yeah, you're laughing because it's true. I don't know why. Somebody pointed that out in an assembly when I was in junior high, and I couldn't help myself. I still did it, even though I became aware of it. So oxygen by itself is going to take a friend. Is oxygen by itself here? No, it's in this crowd. It's on a group date or something here. There's a whole bunch of people here. So it does not need to be O2. The 2 is only when oxygen is all by itself, okay? So it's just O here. Okay, so we've made our path. We've got 3 conversion factors, and so we can write out our formula. 7.2 grams, Al2SO4, SO4 2, and 3 conversion factors, so 3 fractions, and grams of oxygen ends up being over there, moles of oxygen is there, and moles of the big old mess is in the middle. And then we've got grams down there, moles of the compound. Writing out all these formulas is tedious. It is. Just deal with it. Failing the course and taking it over again is more tedious. Think of it that way. It's true.
The grams of AO2 is 414.08.
414.08. Thank you. So this is, she did the calculation for us. This is the molar mass of aluminum sulfate. That many moles per gram. Oh, you did nitrogen instead of sulfur? Okay. So it's always a good idea to check things, right? So let's go ahead and check. 2 times 26.98, that's aluminum. And there's 3 sulfurs, 32.07, and a whopping 12 oxygens. Yeah, so 342.17 grams per mole. Everybody makes mistakes. You've already seen me make mistakes in class today. And I post my mistakes on YouTube. And anybody in the world can watch them. Because we're all human, right? We all make mistakes. So there's no point in, trying to hide that fact. Nobody's going to believe it anyway. So that wasn't quite right. That's okay. I'm just going to erase that. We can even make mistakes when we write this out and calculate it, because we can punch a number in our calculator wrong. You think you hit the 6, but the calculator said, no, you didn't press that hard enough, right? So anytime you're concerned with getting the right answer, which is like almost all the time, right? Punch it through your calculator twice. If you get the same answer both times, you probably got it correct. Or you're really consistent at making mistakes, which doesn't happen too often. If you get a different answer, do it a third time. And hopefully the third one will agree with one of the others and you'll go for best 2 out of 3. Okay, so we've got that. Does anybody else do the calculation? Did I do it right? Okay. So where does that go? The first one. So here we have moles of aluminum sulfate to grams of aluminum sulfate. So that goes in the bottom here. And we put, I put all the units in first, and sometimes I didn't leave enough space. It's okay, you can just kind of squish them in there. So there's the molar mass of aluminum sulfate. This one over here is also molar mass. That's easier because it's just on the periodic table, right? So oxygen, 16.00 grams for 1 mole of oxygen. The mole to mole thing here comes from this chemical formula. So in one formula unit, how many oxygens? 12, right? 3 times 4. So there are 12 moles of oxygen in 1 mole of the compound. It's right there in the formula. So 7.2, I'm going to divide by 342.17 times 12 times 16. And so she got 4.0401, and I'm getting the same thing. So we want just two significant figures, right? Because it's 7.2. So 4.40, and then if we keep going, it's 0.97. So that would be 4.0401. I only need two, though, so I'm going to call this 4.0 grams of oxygen. Any questions?